this unit that we're working on is about regression, right? So regression and scatter plots. So we're going to look at the beers versus blood alcohol content of certain students selected from the University of Ohio in a second. I wanted to look a little bit more at the theory of finding a least squares regression line first. That's a lot of words, right? Least squares regression line. Regression, as you guys read in your reading guide, is just a name that was kind of developed in the late 19th century to describe fitting trends with functions, like the first function we'll be using, the line. And you might think, well, lines are really simplistic, but it turns out a huge amount of data in the real world is actually linear in nature, so it's not as simplistic as it might seem. And what we're going to do here kind of by messing around, we'll try to find the best line by messing around, is not perfect. You need Calc 3 to do this perfectly. So the theory behind how your calculator finds linear regression lines when you press second calculate find the line is based on Calc 3. It's not hard Calc 3, but that's how high the level is. Why is it Calc 3? Because we're minimizing the squares. We're finding the least amount of squares of something, which we're going to look at with this applet. Calculus shows you how to maximize and minimize stuff. We have 2 dimensions, that's 2 variables. It means it's multivariable calculus. So we're not going to do the calculus. We're just going to mess around with it first. Here's a scatter plot. What's this scatter plot describing, guys? Foot length and height. And notice this applet works so you can put your own data in, like the data we just have if you want as well. So it's pretty fun. Let's not show the true regression line obtained via calculus yet. Let's try to fit it the best we can. So there's a line. Do you guys think that straight across blue line captures the trend of what is happening in this situation? If so, I don't know what to do. How do I need to move this line? I see some hand signals. How would you describe it in words? Good, I like the hand signals. It needs to be increasing. I like it. It's got to have a positive slope. There we go. So like this, right? Like that. Jesus. That's a little better, right? Is that the best? The best one that calculus could possibly obtain. Well, we're going to press the button and see how good we did in a second. But the idea here is that you want to have it not just in the middle, but it needs to be in the middle in a very specific way. It needs to be in the middle such that the squares that are created from each data point, so you draw a line to each data point, that's called the residual, which is going to be very big for us as well. You look at the residual, the distance between, for instance, this and the line that you think you want, and you look at the square created by that, and then you think about all the squares for all the points, their overall area, and you try to minimize that overall area, and that gives you the exact best possible answer. Let's try to do it by guessing. We probably could use some squares though, right? I think this applet shows you the squares I'm talking about. It shows you the residuals. Here's what I mean by residual. That's a visual you should remember. We're going to use it a lot. Residual is the distance between the real thing and the guessed thing on your line. The squares I'm talking about for least squares regression are these. Can you see how they created a square with each residual? Now we want the sum of all those squares to be the smallest it possibly can be. That's the best fit that you can come up with. So we can start tilting this line and see, we're getting a lot of residual from this one and this one, right? A lot of area. So I'm going to tilt it. You guys think that's better? It's hard to say, right? Like this is really hard to visualize, but like that, if you go like something ridiculous like this, you can see there's lots of big squares. So we want lots of small squares. It's getting better. You guys see how those ones in the middle are shrinking? Shrinking, shrinking. The other ones are staying about the same. Shrinking, still, oh, they're growing a little bit. I think it's somewhere in there. Tough call. Where is it exactly? Wow. Pretty close, right? So that takes a little bit of experience to obtain, but that's the goal of what we're trying to do when we create a least squares regression line. So let's go back and create the regression line for our calculator. So if you haven't done it yet, here's how you do it. If you see it in the corner of your eye, just tell me. Okay, so first you want to load your data. We're looking at blood alcohol content in the Y and number of beers consumed in the X. Then you want to go second stat plot. Turn a scatter plot on. That's a histogram. Scatter plot's the first one. List 1 and list 7? No. Need to make sure that's list 2, so make sure yours says list 1, list 2. Sometimes we're going to change it. We might use list 3 and 5 sometimes. Pick your favorite scatter plot dot. I like big ones. And press zoom what? Yes, zoom 9, the thing we pretty much always use in here. And you get a picture of your scatter plot. So the first thing that any good AP statistics students knows is how to describe a scatter plot. If you have one adjective describing it, that's worth nothing on the AP exam. If you have two adjectives describing it, that's worth nothing on the AP exam. All scatter plot descriptions should be 3 parts. So, 3-part, and I'd write this on your handout, 3-part description of a scatter plot. We need to describe, and I think you guys had this in your reading guide, didn't you? What 3 things do we need to describe? Strength. Logan's given me one. What else do you need to describe? Direction. Thank you, Lauren. And what else do you need to describe? Form, unusual shape. You could say that lots of different ways. Basically, is it linear or not? Because we're going to see lots of data sets that are not linear, and we'll have to fit them with other kinds of functions, like logarithms or parabolas or things like that. So, is this one looking straight to you guys? In general, now, if there's a couple little things that make it look not straight, that's okay. You're thinking the general trend. Does it look straight?
Yeah.
Yeah, we could like try to draw in the line of best fit, something in the middle, right? So I'm going to say the association between beers consumed and blood alcohol content. You could say for students at Ohio State in this study or whatever, but if you want to use the nice, easy way to never miss points on the exam, you say for students like, yes, for students like these, put commas around that, it's a little clause, right? What is that association? What do you guys think? Is this strong? Is this weak? We're going to be practicing a lot. Is it kind of in the middle? It's pretty tight fitting around the line that would be in the middle. So I'm going to call this moderately strong. There's adjective 1 that I was talking about. Moderately strong. Direction? Positive. And appears linear, right? If it was bent, we'd need to say it was bent. There's another thing. If you use the word correlation and association, be careful. Association describes any kind of relationship. It doesn't have to be linear like this one. If you use the word correlation and then you talk about how it's bent, correlation implies straight. Whenever you say that word, you're implying straight. And that goes for all social sciences. You've heard the word correlation a lot, right? If someone ever uses that word to describe something that's not a straight relationship, they're not using it right. So that's a key thing. That's just a little technicality, okay? So we need to create the regression model. And we need to know how strong. We just said, yeah, it's kind of strong, right? How strong? What we came up with yesterday when we went over how to find R by hand was a measure of how strong. Let's do that again. Let's do it the long way, and then let's do it the short way. On the AP exam, you're always going to do the short way. But it's important, I think, to understand how to use list computation. So let's go through that one more time. And I taped the one yesterday, so you've got that one too as soon as I load it today. So, R, I think it was the sum. Diagnosis for how strong? was the sum of the z-scores in the x direction times the z-scores in the y direction to kind of get a sense of how each one varied about the line. And then I think we had to divide by n minus 1. Is there anything else in that formula? I don't think so. You could simplify it and say, well, z-score, what's that mean? It means x minus x bar over the standard deviation of the x's, y minus the average of the y's over the standard deviation of those y's, all divided by n minus 1. So that's what we're going to do in our lists. My data is already in my list. So list 3 will do z sub x. Oh, but don't I need the average stuff first? Let's load that up. So I better compute that. Where do I go? Can you guys remind me? Stat. Calculate some stuff. What do we want? We want the statistics for 2 things. If you go 1 thing, great. You'll just have to do it again. 2 things. You might have to like scroll down your menu and hit enter a bunch of times, right? Okay, there's our stuff. Let's write it down just in case we lose it. So x bar for our blood alcohol content data was 4.8125. You know, I'm going to say beers on there. That was the average number of beers they made these kids drink. It's a suspect study, but oh well. SX is 2.19. It varied a lot. You guys see that? I can just look at this. I didn't even look at this before I entered class today. And I could see they made them drink quite a bit on average. And some of them really drank a lot because the standard deviation is 2 beers, right? So 2 standard deviations up is kind of rare, but that's like already like, it's like getting a little dangerous depending on how long they did it in. You guys don't know. Y bar. Oh, I didn't just scroll down. Okay. Oh, I went too far. There it is. So the blood alcohol content varied on average that much. And it had a standard deviation of that much. I should say that was the average. This is how much it varied on average. That's how you say that. Okay. Now, you can write those down and like use your, just type them in manually, or you can use the slick way I showed you yesterday. I think you're going to want to learn the slick way for various things. It's up to you though. I don't care. So I'm going to go back to my lists, and here comes the x. So parenthesis, just like my parenthesis on the board, right? The x's are in list 1. I subtract x bar, so you could type 4.8125, right? It's out on my home screen. So I'm going to go vars, stat, there's x bar. If you get something that says error, that means it's like not out on your home screen. It has to be loaded there so your calculator can find it. So hopefully I didn't delete it. We're going to find out in a second. Let's find out. The moment of truth. Did I delete it? I did not. It's still out there. There's all the zx's. Same thing for the y's. Each y is in list 2. The average of the y's is y bar. And I want to divide by the standard deviation. Again, if you just want to type those numbers in up here, do it. I don't care. And then we're supposed to multiply each one together before adding them, right? That's what the formula says. So list 5, I'm going to multiply each one, all the list 3's, by all the list 4's. That's where my z-scores are. Gives me a bunch of junk. And I go out on my home screen and add it all up. So where do I go to find the sum function? Remember, you shouldn't be looking all over your calculator. Almost everything in this class, almost, happens on 2 buttons. Vars and stat. I think you go second stat, because it's a list operation. And then just look around. If you get lost, try again. Quit, try again. Look around. Until you find something that says sum. I see it right there. We're adding up everything in list 5. Okay, we're done, right? There's R. No. If you get something like 13 for R, like on a test, I'm going to be like,
That's pretty strong.
that's pretty strong. You're 100 and at 1,300% sure that this is the right data. What the heck does that mean? Wow. Right? Like it's got to be between -1 and 1, like we said yesterday. So I got to divide it. I forgot to divide by what? N minus 1. And what's n for the data you guys had? 16. Now yesterday we weren't sure. Was it 16 or 32? How many pieces of data do we have here? Well, it's not one variable data. It's two variable data. It's pairs. How many pairs? 16. So we divide by 15. Then we get something more reasonable. So now we can go up and clean this up a little bit and make it better. The association between beers consumed and blood alcohol content for students like these is moderately strong with, and here's how you really explain R, with R equals 0.894. Now this is a run-on sentence. It's awful, right? So usually you'd write two sentences. You know what? I'm going to just continue down here. So we know that blank percent of the variation in the blood alcohol contents that were measured by the breathalyzer can be explained by variation in whatever they did to these poor kids. How many beers they made them drink. The question is, what goes in that blank? I think that was in your reading guide too. Let's see if we learned. What is it? Do you say 89.4% here? That's a fine guess. But if you're going to describe, use this description. You can't use R. You've got to use R squared. So I just explained to you how to explain what R squared is, which is even a better way to diagnose how good your model is. 0.89 is pretty strong. We said moderately strong. I think we were on target there. It's not super strong. It's not 95%. But the percent that you can put here has to be R squared. So I'm not going to get into why that is today. I'm just explaining it. So how do you get R squared? Well, square it. You guys square it for me?
0.799.
0.799. Why'd it go down?
Because you're squaring.
Numbers less than 1, square them, they get a little bit smaller, right? So what I should put here is 79.9%. This is a key thing to know, definitely. We learned a lot of really important stuff today. 3 ways to describe something, and a real specific way to use a diagnostic tool, R squared. R squared means the percent of variation in the y's, and this is what you should memorize, that can be explained by the percent of, by variation, whatever your data was varied like, in the x's. In other words, another way to say this is 79.9% of the variation in the y's can be explained by what we did when we made that line. Does that make sense? So that's a good numerical way to describe how good it is. 80% of what happened is explained by our line. That's another way to say it. It's not good enough, but it gets the point across, right? Okay. So I'm going to pause this bad boy. So we're still looking at that same one, but in general, how do you write a linear regression model down? Of course, it's got like mx plus b, right? Like it's a line. Mx plus b is a line. But what symbols did they give you? Because those are the ones that you'll be given on the test. And they're named that way for a reason too, which you'll see over the course of the year. Mx plus b written in the stats book was y hat equals what? You're going to have like b sub 0 plus b sub 1x. Don't think this is new. It's just a different way to label the slope and the y-intercept. Okay? There's a couple ways to obtain that. You can do the calculus, which our calculator does, and we'll do that to obtain the model for ours. Or you can do like we're going to do tomorrow. Sometimes you don't even have access to the raw data. You just know some statistics, like x bar, and the standard deviation of x. So you can get this using your calculator, which She does calculus to obtain it. Or you can get it like this, and this is one of the AP exam's favorite tricks, is that you can also get the slope by looking at r times sy over sx. You can also get the y-intercept by looking at y bar minus that thing times x bar. Now, where do these little shortcut formulas come from? They come from a lot of math. The book has a 2-page explanation on it. I'm not going to go over that because it's a lot of math. And do you really need it for the AP exam? No. It's definitely something to look at. So you explore that on your own. It's up to you. There's a math box that explains how this other way of obtaining the slope and the y-intercept, where it comes from. And it's a very great explanation, but it would take us like at least a whole class period to go through it. So since you don't need it, I'm not showing you. If this was a calc-based statistics class, I'd show you. Does that make sense? So 2 different ways. Let's do it the fast way with our calculator. So most of your problems, here's how you're going to find r. We've still got that data in there, right? We know r was 0.89. Go to stat, and where do you calculate models? I think you guys have done this before. Calculate. What kind of model do we want? A linear regression model. It's in 2 spots, by the way. It's at 4 and at 8. It doesn't matter which one you use. Which one matches our book's notation? Number 8 does. Does it matter? No. Use the one you like. You can tell it list 1 and list 2. If so for some reason you have them in other lists, you got to say other lists, but you can just hit enter too. It's up to you. There's like everything. Did we get r correct when we did it the long way? Yeah. Wasn't that the r squared we said? 79% of the data, the variation in the y's, the blood alcohol contents could be explained by our model.
Have r squared.
Yeah.
If yours doesn't have r squared, here you go. Go to mode at the top and look around for something statisticky.
Sticky.
I know that's not an adjective, but I don't see anything.
Stat wizards.
What is this? Stat diagnostics? Isn't like R a statistical diagnostic? Yeah. Yours wasn't on, if you weren't seeing it. So if you just run that again, stat, calculate, linear regression, it should show up. If your calculator resets, like you lose batteries, you'll have to do that again. So that's why, good question. Addressed it, now you know where it's at. Okay, it not only told us R right there, it told us the actual best line that it used calculus to obtain. It says it's 0.01796 x plus, minus 0.0127.
So it's like
It's basically just mx plus b, yeah, right? Like, I didn't use this form, but whatever. It's mx plus b. It's a line. It's not that hard. Don't make it hard. How it came up with these is hard. Kind of. So, yeah, there's your line. How do we know it, like, looks good? Can't we, like, go put it on our scatter plot and see if it looks good?
Yeah, just type it.
Yeah, let's do that. You can do it the fancy way or the typing in way. It doesn't matter. So, definitely. But before we do that, or you guys can do that while you're listening, this wouldn't be accepted by the AP exam because it's completely contextless. Does that make sense? So here's how I want you to write it. What is the y in this situation? If we were writing this down on our paper, we'd have a scatter plot over here, right? We'd have it labeled with blood alcohol content and beers. That's always my cheater. I always go back and look at my scatter plot. If it's labeled, it'll help you out. Watch, it's going to be key. So what should I put here? Instead of y, I should put blood alcohol content. And this isn't the real y, is it? Is this like the actual y that exists that explains every possible variation in blood alcohol content? That's why this symbol's on it. That means approximate or model. So I should have a model, and I should say the blood alcohol content model. And I know I'm sounding stupid, but I'm trying it. I know it's the end of the day. And instead of X there, I should put what? Beers. That's right. That's a professional AP Stats level regression line. And we already talked about it, right? We said, yeah, it's a line. We said it was moderately strong. In fact, that strong, that percent of variation explained, blah, blah, blah. Of course, it's positive, right? This tells you positive or negative as well, right there, right? It's positive. So, okay. If we missed anything else, I think we're good to go. The only thing we haven't used yet, which we'll use tomorrow, is what if you don't have the data? We have the raw data. What if they just tell you the standard deviations and the averages for each set? Do you need the raw data? Those say no. So we'll look at these in an example or two tomorrow and create a regression line, mx plus b, that way. Okay?